Hey folks, so I want to do a few quick examples going over sequences and whether they converge or diverge. So for this first example, we're given a list of numbers, and so our first thing we're going to want to do is transform this list into a nice clean formula. Again, we're going to look for patterns and see if we can describe those patterns as functions we recognize. So for example, that numerator, I'm seeing a pattern here where, let me just go ahead and highlight those. 1, 4, 9, 16, 25. I recognize those as perfect squares. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Okay, so it sure looks like that numerator is a bunch of n squared looking things, right? So here I'm making an assumption that my sequence is going to start with n equals 1 and then go to n equals 2 and so on. Okay, but then my numerators are all n squared, and that's great. So let's look at my denominator next. I have 2, 3, 4, 5, 6. Okay, so it's counting up by 1, but notice I can't put n on the denominator, right? Because if I put n here as my denominator term, then right, this wouldn't quite match, right? N equals 1, but it's actually 2. So we see it's always one more than the n, right? It's 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, 5 plus 1. So, for whatever n you give me, it's actually n plus 1 in the denominator, right? It's always one more. And the last thing I'm missing is I'm noticing an alternating sort of coefficient here, the plus, minus, plus, minus, plus. And you might remember in class, we talked about a way of getting this alternating plus, minus is using minus 1 to the n. Okay, so let's see, how do I get that minus 1 to the n here? Well, if I just multiply it, and now you always want to check, right? Do I have the right sort of order of this? Is it plus, minus, or is it minus, plus, minus, plus? So if I try to plug in n equals 1 to start, it'd be 1 over 2. But then the 1 here would make this minus 1 to the 1, which is negative. And aha, I want to start with a positive, actually. So because I'm off by 1, let me make this n plus 1 instead. There we go. Okay, so now this does a nice job of capturing my sequence. So my sequence can be written minus 1 to the n plus 1 times n squared over n plus 1. And again, for this sequence, we're starting at n equals 1, just to be really clear. Okay, so that's the first step we might want to do is just transform this into a nice clean formula. And the next thing we want to do is see whether or not this sequence converges. And so remember, that just means let's check the limit as n goes to infinity. I want to know as I take larger and larger n values, as I go further out in this list of numbers, does it approach any particular number? And so when I look at this, I see that negative 1 to the n plus 1 expression, which to me really screams squeeze theorem, right? Whenever I see alternating sort of behavior in my sequence, I'm thinking squeeze theorem. So let's see if it'll work. Let's try to apply squeeze theorem here. Okay, so remember the idea here is I'm going to have my sequence, my original sequence, the one I care about. I'm going to try to squeeze it between two other sequences, which are hopefully easier. Well, remember the idea here is, the problem point is this negative 1 to the n plus 1. And so the thing that I'm going to bound above it, right, I'm going to say it's less than or equal to something easier. Well, the easier thing to do is just make all of these plus ones, right? In class, we said just take the absolute value, right? Make this absolute value, make all of these plus ones. And so this will become plus 1 n squared over n plus 1, right? And these are always bigger than or equal to the original expression. And sort of by similar logic, on the left, what I'm going to do is take all negative ones instead, right? Make it always negative 1, negative 1, negative 1. And that's always less than or equal to the true sequence. And so that'll be a lower bound. So negative n squared over n plus 1. Okay, now these two sequences I'm looking at look a bit easier. Let's ask that question. What happens as n goes to infinity? Let's start with that right sequence. So n squared over n plus 1. What I'm noticing though is that numerator is growing at a faster rate than the denominator, right? We could use, for example, L'Hopital or division by n on numerator denominator to sort of check this rigorously. But I can see from inspection that this is going to grow to infinity, okay? That n squared beats the n. And by similar logic, the expression on the left, this lower bound as n goes to infinity, that's going to blow up to negative infinity. Now, this is kind of interesting. What does this tell us? Well, it tells us that we can't actually apply the squeeze theorem here, right? The squeeze theorem doesn't work. Why not? Well, remember that the squeeze theorem, in order for it to work, we need to make sure that upper bound and lower bound sequence both converge to the same number. And in this case, they both diverge to opposite infinities, in fact. And so we can't apply the squeeze theorem here. And in fact, after a moment's more thought, we see that this sequence, in fact, diverges. Why does it diverge? Well, think about what we learned from our little exercise here, right? We saw that these positive terms are growing to positive infinity, and the negative terms are going to negative infinity. And so our sequence is kind of bouncing between those two extremes. It's the n squared plus, so the n squared over n plus 1 part is getting bigger and bigger and bigger, and it's alternating plus minus plus minus. So our sequence is going to do something like this. It's going to get bigger and bigger and bigger and go plus minus plus minus. And yeah, this isn't going anywhere. This is diverging. Very interesting first example. Let's go ahead and try a second one. Suppose I'm doing the limit of this sequence, n squared times e to the minus n. Well, let's compute the limit as n goes to infinity of this sequence. In this case, I don't see any alternating behavior. I don't see a minus 1 to the n or anything like that, which means I'm going to try to use my regular limit law approaches to solve this limit. So first thing I'm going to do is just try to plug in, right? Plug in n equals infinity. I get infinity squared, which is infinity, times e to the minus infinity, and well, that's 0. So this is infinity times 0. Aha, this is indeterminate, which means I should be using L'Hopital. Okay, so in order to use L'Hopital's rule, remember I'm going to turn this into a fraction. So I'm going to bring the e to the minus n to the denominator, make it e to the positive n. And now this is infinity over infinity, which means I can apply L'Hopital's rule and get the following expression. So derivative of n squared becomes 2n. Derivative of e to the n is e to the n. Now I evaluate this limit and, okay, it's still infinity over infinity, which means I should use L'Hopital again. So now one more application of L'Hopital's rule gives me 2n becomes 2. E to the n stays e to the n. And what am I left with? Well, 2 over e to the infinity, which is 2 over infinity or 0. Hey, guess what? This sequence converged, right? We saw that this sequence, if I plugged in larger and larger n values, is getting closer and closer to 0. Okay, this is a nice contrast to the previous example. In this case, we didn't have to use squeeze theorem. We're just using our regular limit laws, and in this case, L'Hopital's rule to evaluate the limit. All right, last one. Ooh, an interesting looking one, sine of n over n. Now, let's see what we can do with this. Let's try to take the limit as n goes to infinity of sine of n over n. Now, a lot of us are going to want to try to use L'Hopital's rule here because you're seeing, oh, fraction of things. But that's not going to work, right? Why not? Well, for me to use L'Hopital's rule, I need to have an indeterminate form, right? 0 over 0, infinity over infinity, 0 times infinity. And guess what? When I try to plug in infinity here, none of these things happen, right? What's sine of n as n gets bigger and bigger? Well, the sine function just keeps on going up and down, up and down, up and down, right? There's no limit for that. It's not infinity, it's not 0, it's nothing. It doesn't have a limit. So L'Hopital does not apply here. I can't use L'Hopital. Can't use it. Okay, so then you say, what do I do? Well, I gave you a hint already, it turns out. The sine function is oscillating up and down, up and down. So whenever I see oscillations, so sine of n oscillates. Whenever I see oscillations, I think squeeze theorem. Squeeze theorem is the way out of this. Okay, let's see why. Sine of n over n. Okay, well now I need to figure out how to get an upper bound for this. Well, It's not so simple as just take the absolute value anymore, right? I mean, it's just absolute value sine of n over n. What does that mean? Now, what you want to think about is, here's the easier way to think about this. The sine of n term is the term I don't like. I want to try to get rid of it, make it simpler. And so what can I do to do that? Well, let's ask, what is something that's bigger than sine of n? Well, if you think about the picture, right, think about the graph of sine for a moment. Looks like this, right? And what you notice is there is always an upper bound that sine will never go above. And that upper bound is 1, right? The sine function, no matter what you plug into sine, it's always smaller than 1. And so guess what? I'm going to say that sine is less than 1, and then the n I'm going to leave by itself. And if you take a moment to think about this, you'll see this is always true, right? That no matter what n you plug in, sine of n is, it's between -1 and 1, so it's got to be less than 1 over n. Wonderful. And now using the same logic, right? Using the same logic, what's something that this expression is bigger than? Well, the sine function is also always bigger than -1, which means I could put -1 over n as a lower bound for this, right? The sine function will never be smaller than -1. And guess what? I've now squeezed my sequence between two simpler looking sequences. And now we can try to see what happens as n goes to infinity in these sequences. Well, in this case, it's a little bit easier. I see 1 over infinity just goes to 0. -1 over infinity, hey, that's also 0. Aha. In this case, the squeeze theorem does work. Since both the upper and lower bounds, both of those outer sequences converge to 0, we know by the squeeze theorem that the sequence in the middle, our sequence, also converges to 0. And now it's kind of nice to see a picture of this just so we have a sense of what's happening. That sine of n over n, it's going to look something like this, right? It's going to bounce back and forth, but it's always sort of getting closer and closer to 0, right? As you go farther and farther out, these dots are getting really, really close to 0. Even though it's bouncing above, below, above, below, above, below, every term eventually gets really, really close to 0. Okay. So I hope these examples were helpful. If you have questions, definitely let me know, and I'll see you in class.